Alright, so now that we have finally wrapped our heads around big O notation and understand how to mathematically rate our code's efficiency, it is time to actually do something useful with it. We are moving ahead to the core algorithmic patterns you'll use every single day to stop your code from choking in production. Think of Big O as the diagnostic tool and these patterns as the actual weapons in your inventory. And the absolute first pattern we need to master, the one that shows up everywhere, is the hash map. Let me just give an overview of how this will play out in real life. You build an app locally, the UI is incredibly clean, the animations are buttery smooth, and everything works flawlessly on your machine. You put it to production, and things look great at first. But then the database grows. Instead of 5 mock items you used for testing, you suddenly have 50,000 real data entries. Suddenly, users start reporting that the app slows down to a crawl the moment they try to filter or search. The screen stutters, the dreaded loading spinner stays up for a few seconds too long, and the client devices start running hot. This isn't a framework glitch or a UI bug, it is an algorithmic issue. It means somewhere in the codeways, a nested loop is violently searching through an array, consuming CPU cycles because it scales terribly with data growth. Today, we're fixing that. When textbook authors or interviewers talk about hash maps, they throw around dense phrasing like constant time lookup design using key value pairing or map or set structural counting. Let us translate that into plain English. In a standard array or list, data has no inherent address. If you want to find out the number 8 is on the list or not, of 1,000 numbers, the computer has no choice but to start at the index 0, read the value, move to index 1, read the value, and check every single slot one by one until it hits your number. That is O of n time. The time it takes grows perfectly linear with the size of your data. A hash map changes the rules of data retrieval entirely by using key value pairs. Instead of just tossing data into an ordered list, a hash map takes a unique identifier, the key, and runs it through an internal mathematical formula called a hash function and generates an exact instant memory address where the value is stored. Because the computer can calculate this address instantly using math, it doesn't matter if your dataset has 5 items or 5 million items. You hand the map the key, it calculates the address, and jumps straight to the data in exactly one step. That is what we mean by O of 1, constant time. Now, there is an eternal compromise here between time complexity and space complexity. Using a hash map is deliberate trade-off. You are trading your device's memory to save CPU processing power. You are dedicating a small chunk of RAM to maintain this structured memory map so that your processor never has to waste cycles running repetitive search loops. Look at how the software platforms you use every single day lean heavily on this pattern to avoid crashing under massive user loads. Spotify's duplicate detection. Imagine you have a playlist with 5,000 songs and you try to add another track. Spotify doesn't launch a slow sequential loop to scan every individual song one by one just to see if it is already in there. That would make your phone processor do manual labor for absolutely no reason. Instead, it uses a hash set, a close relative of the map, containing unique song IDs. When you click add, it checks if that ID exists in the set. Boom. Instant check. Uber's live driver coordinates. When you open Uber, the app needs to constantly verify driver availability or quickly pull up specific driver profile locations. It queries data via a massive distributed key value lookup system, reads the unique driver ID as the key, and returns their map coordinate as the value instantly. Okay, now how do you know when to pull this pattern out of your toolbox? You look out for classic linguistic red flags in a product spec or an interview prompt. If you see words like count, frequency, or have we seen this item before, your brain should instantly trigger the Hashmap pattern. But the most elegant way to leverage this data structure is something called the lookup before you write strategy, which completely dominates complement style tracking problems. Let us ground this with a simple real world hypothetical situation. Imagine you are building a budget tracking fintech app. A user sets an explicit spending limit alert for a single shopping trip, let us say exactly $10. They walk through a store, scanning items into their phone cart one by one. The app needs to alert them immediately if any two items in their cart combine to equal exactly $10. Let us say the store items scanned are in an array of 4, 8, 2, 6, 3. If you code this like a standard rookie, you'll use a brute force nested loop. You pick the first number 4, then you run a completely separate inner loop to look at every single other number in the array, like 8, then 2, then 6, and so on, to see if they add up to 10. This gives you a terrible quadratic O of n square time complexity. If that user scans a large grocery haul of 1,000 items, your app is performing up to 1 million operations just to check a basic sum. Your phone's battery will start cooking an egg in the pocket. The UI will lock up entirely. Instead, we use the Hashmap complement trick. The math equation is remarkably straightforward. Target minus current value is equal to the complement we need to find. Let us track this step by step using an empty Hashmap structure we call seen before. Step 1. We see the number 4. The app computes 10 minus 4, that is $6. We quickly ask our Hashmap, hey, have we seen a 6 before? The map checks its memory in O of 1 constant time and says, nope, nothing in there. So we save our current number 4 into the map as a key and move on. Step 2. We see the number 8. Complement needed, 10 minus 8, 2. We query the map. Have we seen a 2? Map says negative. We write 8 into our map. Step 3. We see the number 2. Complement needed is 10 minus 2, 8. We ask the map, have we seen an 8? And the map instantly replies, yes, we actually processed an 8 back in step 2. Your app immediately fires the alert notification. We found a matching pair, 8 and 2, in a single linear scan through the dataset. You didn't double back, you didn't rewrite data, and you never ran a single nested loop. Let us read this code directly, line by line, so you can see how straightforward the execution flow is. First, we initialize a fresh map object called seen before. Then, we kick off a standard sequential for loop over our input items array. Inside this loop, we calculate our complement needed value on every iteration. Notice the architectural placement of our conditional statement. This is where the magic happens. This is the explicit execution of our lookup before you write rule. We check the memory tracking system first before we modify or save anything down. Because checking a key inside a map structure relies on a highly optimized internal hardware hash function address jump, this conditional check runs in instantaneous absolute O of 1 constant time. If the map confirms the complement value exists, we immediately return the pair. If it doesn't find a match, the fallback line kicks in. We gracefully save the current scanned value as our key and store its index relative to the input array. Let us review the final efficiency rating of this optimization. Because we have completely bypassed nested loops, our total execution time scales directly in a 1:1 ratio with the size of our dataset. If the array has n items, the loop executes exactly n times. This elevates our solution to an ultra efficient O of n, linear time complexity. You just converted a potentially lagging user experience into a production ready bulletproof architecture. To sum it up, learning Hashmap is just about writing code that doesn't slow down when your data grows. But getting comfortable with these patterns takes a bit of time. We aren't going to jump straight into grinding 50 different lead code problems right now. The goal of this series is to get through the core patterns first. Once you actually understand how these patterns work under the hood, spotting them in real problems or interview becomes a lot easier. In the next few videos, we are going to cover the other common patterns you'll need. Now you know the drill. If you don't want to wait for videos, the resources are in the description below. See you in the next one.